Today we're going to start a topic about gradients on curves. Now, what does that mean? We know when we have a graph a bit like this that the straight line is described by y equals mx plus c, and m is the gradient. But other functions, let's look at the sine curve, for example. Okay, they have a changing gradient. You can see here, at this particular point, the gradient's positive. And I could actually work that out by drawing a tangent and then doing rise over run. If I move along a little bit here, then suddenly it's negative. So you can see it's changing throughout. And what we're going to be interested in is calculating these changing gradients. That's essentially the main aspect of this topic. And I've got to say, this is my opinion, but I've got a lot of reason to say this. This is one of the most important discoveries in maths ever made, and that makes it one of the most important discoveries ever made because maths underpins science, essentially underpins technology. And this interesting scenario where you're actually just calculating the gradient turns out to be ridiculously important. But that's justification for that I might leave for now, but I just wanted to say that at the start. We're going to have a go at calculating the gradient on a curve that's not a straight line. So let's look at y equals x squared. Okay, this graph looks a bit like this. I'm only going to draw it for the positive quadrants, positive values of x and y. Okay, and then what I'm going to do is I'm going to set it up, and I'll explain why I'm doing this in a bit, but I'm going to choose the point 1.5. I just happen to have chosen that. And that's the point that I want to find my gradient at. Now let me say this. So this is this is essentially the gradient, the instantaneous gradient, the gradient of this tangent that touches it. Okay, but the question is, how are we going to do that? How are we going to calculate it? Well, we're not going to be sort of drawing tangents in our mind or anything, or going that route. We're going to go a slightly different routes. We're actually going to draw points that's slightly further away to start with. And let's say it's 1.5 plus a small amount. And I'm going to say it's plus h, where h is a small number. Because where we're going to be going is, obviously, if this point is really far away, then it's not going to represent the gradient of the curve, because you're going to be finding the gradient of this point. That's what we're going to be interested in doing. But if we move the point closer, and we're going to be doing that in a bit, then actually it looks a bit more like the gradient at the curve. And if I move it really close, then actually it's going to approximate the gradient at that point. So that's the thinking behind this. But for the time being, we're just saying it's some distance h away, and we can then change what h is at a later point. Okay, so actually, at the moment, we are finding the gradient of this. We're going to be interested in finding the gradient of this chord. This is called a chord going between 2 points. A chord is not only applied to a circle. I'm just going to write that down because you spell it like this. Okay, now I've got the run actually already. I've gone along by h. That's going to be the difference. So if I can get the rise, then I can work out the gradients. And I can do this by just substituting it in to the equation. So this is going to be 1.5 squared. And this one is going to be 1.5 plus h squared. I've just taken my x value and squared it. So what does that mean the rise is equal to? Well, it's going to be 1.5 plus h squared minus 1.5 squared. And we have the rise and we have the run. So my next step is to write that down. I can write down that the change, this is notation you may have seen before, the change in y over the change in x, which is equal to the rise over the run. I'm going to write it in words as well. Well, that's going to equal 1.5 plus h squared minus 1.5 squared, all divided by h, the run. Okay, so hopefully you can see where I'm going with this now. I'm actually calculating the gradient of a chord. It's in terms of h. I know this little distance away, but I've drawn this little triangle to work out the rise over the run. Okay, what next? Well, I can try expanding this out. So this is a double bracket. It's going to be 1.5 plus h times 1.5 plus h minus 1.5 squared. I'm not going to worry about what 1.5 squared is for the moment, all divided by h. And now I can expand this bracket. I'm going to get 1.5 squared, and then I'm going to get 1.5h, but I'm going to get another 1.5h here, so I'm going to get 3h, and finally I'm going to get plus h squared. I still need to minus that 1.5 squared, and I still need to divide through by h. Now notice, this and this cancel. They're gone from the formula. And there's one other thing I can do, because now we've got rid of the numbers, I've actually got a common factor of h in here, and I can cancel that out as well. Now there's two ways to do it. The first way is to realize we can factorize out the h and write h3 plus h over h, and then just cancel these to leave us 3 plus h. You can just sort of do it directly. You can divide this term by h and then this term by h as well. But you have to, because there's a plus there, you have to divide this one by h and this one by h. In any case, we get 3 plus h as our answer. So actually, whoa, let's just think about this. We had this quite complicated formula, but we have just shown that the gradient at a point x equals 1.5 on the curve y equals x squared is 3 plus h. So it's momentarily 3 plus h. And then it's obviously just after it's going to change, okay? So this only applies for 1.5. Now here comes the most controversial bits, okay? And I'll talk a little bit about why. What we're going to do is we're going to let h not equal 0, but approach 0. Because at the start we said it's some distance away, but we didn't say how far. We can actually control it. And we can basically make h smaller and smaller. So I can move it closer and closer and closer and closer. And as I said at the start, I can essentially make it so it's the same point. It's technically not the same point, but I can make it as close to the point as I want to. So let h tend to 0, then the change in y over the change in x will tend to 3. My h disappears. Am I saying it's equal to 3? Well, I'm not at the moment. I'm saying it approaches 3, but the point is I can get it as close to 3 as I want. And actually, what we say is we say that dy by dx equals 3. So my gradient, this is sort of the gradient that I'm used to, the gradient of a tangent, but I call this the instantaneous gradients. And actually these are the same things. The limit as h approaches 0 of the gradient is actually dy by dx. Now d means an infinitesimal change. I actually think it's from a German word, because this bit of mathematics, this notation we're using was discovered by a German mathematician called Gottfried Wilhelm Leibniz, and the other person who worked on it was none other than Isaac Newton. So these two people pioneered this bit of maths, although there had been people before, as is always the case in research, that had had similar sorts of ideas. But d means infinitesimal. Tiny, 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 as small as you want it to be. Infinitesimal. And what this is not d times y, it's dy, because it's all together. It's an infinitesimal amount of y. I can't just cross these off. That doesn't make any sense in this notation. dy means the tiniest little change in y and the tiniest little change in x. So what we have just shown is that the gradients of y equals x squared at x equals 1.5 is actually is actually equal to 3. It's going to change soon after, but we've now got the ability to calculate instantaneous gradients. This is another word for dy by dx, instantaneous, because a moment before and a moment after it will be different. Let's backtrack. We've just calculated the instantaneous gradient of y equals x squared at x equals 1.5, but there's nothing special about x equals 1.5. I just did it as using a number to start with. So how can we work out the instantaneous gradient anywhere on this curve? Well, for this, we're going to get rid of the 1.5 and we're just going to replace it by x, because then I can say that x can equal anything. I could set it equal to 1.5, but I could set it equal to something else. So I'm going to go through the example again, but changing all my 1.5s into x's. So x plus h, this is then going to become x squared. And this is going to become x plus h all squared. Brilliant. And then I can do exactly the same again. I can just replace all these 1.5s because it'll be the same argument that I'm making to work out the gradients. Yeah, remember it's x plus h squared. I haven't rewritten this one. Let me do that. Okay, and then I can just expand this out, this bracket. But this time when I expand it, I'm going to get x squared when I expand it. And I'm going to get x times h and x times h. So instead of 3, I'm going to get 2 lots of x times h, which I'm going to write as 2hx, because we tend to write the thing that we're interested in like at the end. I could write it as 2xh if I wanted. And then I'm going to be minusing x squared as before. Okay, so it's very similar. It's now purely algebraic. X can be anything. And then what am I going to be left with? Well, again, these are going to cancel. Sorry, that was a minus. Don't forget the minus. So I'm going to get 2hx plus h squared. Two hx plus h squared over h. And this time, if I factorize out a h, then I'm going to have 2x here. And that's going to leave me 2x plus h. Or you could imagine cancelling it out from here. And this is my gradients then. So it's now not at just the point 1.5. Wherever I am with my point x on the curve y equals x squared, the gradient of my chord that I have will actually equal 2x plus h. Now here comes the little trick again. I can make h as small as I want. Then in this case, the gradient will approach not 3, but 2x. So whatever my point is on y equals x squared, the gradient's going to equal 2 times it. So if now I can see that if x was 5, the gradient's going to approach 10. If x is 1, the gradient's going to approach 2. And this just makes sense, doesn't it? Because as x gets bigger, the gradient is increasing. But now we know exactly how it's increasing. In fact, the gradient is increasing linearly. Whilst the function is a quadratic, the gradient is a linear thing. We can even make x negative. When x is -1, the gradient will be -2. This argument will still hold that we're making. And overall, what we say is that dy by dx is equal to 2x as well. And here's how you can write it. You can also say that dy by dx is the limit it's the limit, that's shorthand for limit, that means you're approaching something. It's h tends to 0 of my change in y over my change in x. But we've actually said what that is. In our case, it was going to be x plus h squared minus x squared over h. I'm just introducing some other notation now. So this is exactly what I've been doing, but I did this without really worrying about it. But I can actually write this formula straight down. Why would I want to do that? Because at the moment, although we've been building this up, we've only looked at a single function, y equals x squared. So I want you to think, how could you investigate this for some other function? What if it was something like this? Y equals f of x. Now we're going to go straight into it. We're interested in the gradients, let's say at this point here. How can we write down dy by dx in terms of the function? What we can do is we can say, right, the point is x, and this is going to correspond with f of x. I'm going to put a point a little bit away. It's going to be x plus a little bit. I'm going to call that h, and immediately I have my run, which is h. Now, what's the function going to be at that point? Well, it's going to be f of x plus h. I don't know any more than that. But my rise is going to be f of x plus h minus f of x. Hopefully you're with me so far, because remember, I'm finding, sorry, I didn't draw this on, but I'm finding the gradients of this chord. And then I can say that the change in y over the change in x is equal to the rise of the run, so the rise is f of x plus h. This is why I didn't go straight into it writing this down. It takes a bit of time. Okay, so I did some examples. I've tried to build it up slowly over h. And now, what happens if I want to know the instantaneous gradients? That is, I want to move the point closer and closer. It's not letting me do it on here, but I basically want to move the point closer and closer along here. Well, I'm going to take the limit as h tends to 0 of this thing. And this, ladies and gentlemen, is the formula for how to find the instantaneous gradients of any curve. If f of x is equal to x squared, we get dy by dx equals 2x. I showed that one above. But what if it was something else? What if it was x cubed? What if it was x to the n? This is something we're going to be investigating. I'm not just going to go through lots of examples. I want you to now grapple with this idea of dy by dx and do a similar sort of thing. So I'm going to say to you, have a go now at doing y equals x cubed and finding dy by dx. Pause the video and have a go. Okay, so I've asked you to essentially find the instantaneous gradients of y equals x cubed, a function that looks kind of like y equals x squared, except if you just look in the positive quadrant, but it has a different behavior. It's actually going to infinity more quickly, so it's not going to be dy by dx equals 2x. But let's not worry about the graph now. I'm just going to put it to one side because I've used a general graph to derive what dy by dx is. So now I've got f of x is equal to x cubed. So I've got this bit of the formula sorted. So I just need to work out what f of x plus h is. And that's going to be x plus h cubed. So I've got a cubic to try and work out. I got to expand it out because then I'll see things cancelling. Things will always cancel in these sorts of scenarios. So then I'm going to write it as x plus h, and actually it's going to be x plus h squared, and I've already figured that one out. I did that before, so I'm going to take a little shortcut and not do the whole thing again. I know it's x squared plus 2hx plus h squared. And then what I need to do is expand this cubic. I'm just going to make a bit of space to show my expansion. You have practiced this topic, but I'm just going to quickly recap it. Okay, what we now do, I'm not going to go into detail why we do this, but we just multiply them each by turns. So it's going to be x cubed. You could even use the binomial theorem, actually. I'm not using the binomial theorem here. 2hx squared. You've got to be really careful you don't miss indices. Plus h squared x. Notice I'm putting x at the end every time. Then I do the ones with h. It's going to be hx squared. That was a squared. Let me just sort that out. Plus 2h squared x plus h cubed. Okay, this does not look very nice. This looks much more horrible than the quadratic one. But I can combine like terms, and I'm going to get x cubed. That's, oh, sorry. No, that's okay. I'm going to get x cubed, but then I've got this and this are the same, and that's going to give me 3hx squared. And then I've got this one and this one the same. That's going to give me 3h squared x. And then finally, I add on h cubed. Okay, a bit of effort, but I'm ready now to use a formula. So let's go for it. I think I'm going to go for it and use the full notation. So it's going to equal, and I'll explain each step at a time. It's going to equal the limit h tends to 0 of f of x plus h. That's this whole thing that I've just written down. I'm going to write it down again. Minus f of x. So I'm going to minus that x cubed, and then I'm dividing through by the run. Now look what happens in exactly the same way as before. These cancel. And then look what happens in exactly the same way as before. We've got a common factor of h, which I'm going to factorize out. And again, I can cancel out that h on the bottom. Do you know what? I didn't talk about this before, but the fact is I'm letting h tend to 0, but it's only when I cancel it off the bottom that it's going to work, because if I let something tend to 0 that's on the bottom, like 1 over x, for example, if I let x tend to 0, then this goes to infinity. So I need to cancel out this h on the bottom. That's absolutely essential. And now I'm basically there. I've got the limits h tends to 0 of 3x squared plus 3hx. Sorry, I missed the x out there. Plus h squared. Now what's going to happen as h tends to 0? This is going to go, because I can make it as small as I want. It doesn't matter, x is like got particular value, so when h tends to 0, this is going to go. But this is not affected by h tending to 0, and therefore dy by dx, the instantaneous gradient of x cubed, is equal to 3x squared. And I've worked it out. So now we've got 2 to add. We've got 2 in our list. dy by dx equals 3x squared. Okay, so when f of x is x squared, dy by dx is 2x. When f of x is x cubed, dy by dx is 3x squared. And what I want you to do now is investigate some other functions. And I'm not actually going to give you any examples. I want you to think about it. What could we find the instantaneous gradient for? And the answer is we can find it for any of them, but there are varying levels of difficulty for some functions.